Okay, so we start after having discussed PN junction. Let's next discuss bipolar junction transistor. And bipolar junction transistor, all of you know that it is a three-terminal device. And there's a three-terminal device. And the specific characteristics of not just bipolar transistor, but any transistor, the characteristics that we are looking for is the following, that as we said, three terminals are there. There's an input pair of terminals across which we apply the input voltage, and there's an output pair of terminals across which we measure or we get the output current and the output voltage here. So the specific characteristics of a transistor that we are looking for is an element. It's an element in which the output current is very sensitive to the input voltage and insensitive to V0. That's the specific characteristics that we are looking for a transistor. A output current which is very sensitive to the input voltage and not that sensitive to V0 here. And if you look at it, you're looking for something which is very strange. You're looking for something which is very strange. Why? Because normally, if I'm looking at a current flowing between a pair of terminals here, I would expect it to be very sensitive to the voltage applied across its own pair of terminals and not very sensitive to voltage applied across some remote pair of terminals. That would be the normal behavior of three-terminal devices. It would be sensitive to voltages applied across it, and not very sensitive to something far away, two terminals which are somewhere else. From a transistor, on the other hand, is just the opposite. It's very sensitive to the voltage applied across some remote pair of terminals, and not very sensitive to V0. All right. So what we are looking for then, the sensitivity of I0 to Vin. Let's say the change in output current to change in input voltage is what we call as transconductance. All of you know that change of current with respect to change in voltage is conductance, right? Now, because we are measuring current at one particular pair of terminals and the voltage is across another pair of terminals, the sensitivity of I0 to Vin, we call it transconductance. It's conductance, but trans because the voltages and currents are at two different places. Okay, so that's where the word transconductance comes from. So, and the sensitivity of I0 to V0 itself is what we will call as conductance, normal conductance. And because this conductance is across the output, we call it output conductance. Right? So we have two parameters now with us. One is transconductance, which tells us how sensitive I0 is to Vn. And we have output conductance, which tells us how sensitive I0 is to V0 here. And so what we are looking for in a transistor is an element for which transconductance is much higher than output conductance. That's what we are looking for. Transconductance is much higher than output conductance. So we are looking for an element which has the transconductance is prominent in terms of its value and in terms of its effect. Transconductance is prominent, and the inverse of transconductance is also transresistance, and that's how the transistor gets its name. It's an element where transconductance or transresistance is a prominent feature of that particular element here. All right. So ideal transistor that we can think of is in this particular form here. A transistor, again, a three-terminal circuit, a three-terminal element, and ideal because we said transistor is an element in which transconductance is prominent, output conductance is negligible. So as an ideal element, we've removed output conductance altogether. No output conductance, which means that the output current is simply sensitive to the input voltage and does not depend on the output voltage at all. Okay, in that sense, it's an ideal element here. All of them, all transistors would have some sensitivity to output voltage also. The other thing is the relationship between I0 and Vi, we have assumed it to be linear. So it's ideal in two senses. One is that there is no output conductance, and the other one is that the relationship between I naught and Vi is linear. It linearly varies, and it's ideal also in another sense that there is no input current. If you note that between the pair of input terminals, we have left it open. Okay, so there is no input current. So it's ideal in several senses. And why are we calling it ideal? Anything is ideal only with respect to a certain situation. I'm calling it ideal because such an element would be ideal for making amplifiers. Okay, all right. So these are the elements that you see here. I naught is linearly related to Vi. I naught just depends on Vi, input voltage, does not depend on output voltage at all. And there is no input current here. There is no input current. Okay, so if we take an element like this, so what you can see here is that I'm calling a ideal transistor as nothing but a voltage control current source. If you look at this element, it's nothing but this, all that is there in this particular 3-terminal element is this particular one here, and it's a current source controlled by a voltage here. So we're looking for a voltage control current source. Okay, that's what an ideal transistor is. If you can find a voltage control current source, then there are a lot of useful things you can do. For example, you could build an amplifier. I could take this 3-terminal element here. I could connect a load. I could connect a source. And it's very easy for you to verify. If I connect here and connect in this particular manner here, RL here and source here. So very easy to see that this is nothing but GM times the source voltage here, Vs, and that's going to flow through RL. And the gain of this particular circuit will be minus GM times RL. So, if I'm given a certain value of GM, I can always choose RL sufficiently large so that GM-RL becomes greater than 1 and I get amplification there. Okay? So one can see that if one has an element like this, one can easily connect a load here, RL, connect a source here, and thereby make an amplifier. All right? Now, such an element can never exist, right? Why? Why is it that it can never exist? Look at this element here. What is it violating? Huh? Violating, right? I mean, we are saying that I'm getting a lot of power here. A lot of power here. There's no power from the input. Input is an open circuit. Where is all this power coming from? Right? So it's just a hypothetical ideal element. It can't exist. There's no source of power, and it violates that law of conservation of energy. Right? So it can't be no element can be like this. An ideal voltage control voltage source, it cannot be like this. Okay? So what we can do, what we can perhaps construct is an element which over maybe a part of its characteristics exhibits something like this. Not over the entire behavior, but somewhere in a part of the characteristics you may see a behavior which is like this here. That the current is maybe not that sensitive to output voltage and sensitive to input voltage. So if an element shows over a part of its characteristics this kind of a behavior, where transconductance may be prominent as compared to output conductance, that region of the device, then we could exploit for creating an amplifier. All right. So with that background, let's discuss bipolar transistor. So please keep that in mind. What are we looking for? We're looking for in a bipolar transistor. So if you want to understand why that particular structure that I show you is called a transistor, you should be looking for characteristics like this. Is I naught independent of V naught or very less sensitive to V naught? Is I naught sensitive to input voltage here? So you should be looking for an element which is something like a voltage control current source. That's what it should be there in your mind while we discuss a bipolar transistor. Again, if you recall, our interest is not so much in terms of what is happening inside the bipolar transistor. In this particular course, we are more of users of bipolar transistor. So I can't spend too much time, but I'll nevertheless try to give you an idea of how the bipolar junction transistor works, maybe in 1 or 2 lectures here. All right, so the first thing is This is the structure, schematic. I won't call it a structure, schematic of a bipolar transistor. There is an NPN version with the N side being called emitter, base, and collector. Now, this particular picture is not entirely correct, as you would see, because the emitter is not simply N, but it is N plus. We call it N plus because it's very heavily doped. The doping level in emitter is much, much larger than the doping level in the collector. So bipolar transistor is not a symmetrical device. It's not symmetrical. Looking at this particular picture, I would think it's symmetrical. I can easily change emitter and collector and everything would remain the same. The idea is no. The emitter, this region is heavily doped. The doping levels are 10 to the power 19 or higher. And the collector, the doping levels are much lower. Okay, so it's not a symmetrical device. This is the symbol that we use. So that's an NPN version. And the PNP version is where the emitter is P and the base is N, and you can see the symbols here. The symbols are here. They denote the normal direction of emitter current here. Okay, the normal way in which we operate the bipolar transistor is current would be going into the base, current would be coming out of the emitter, current would be going into the collector. That's a normal operation. Doesn't mean that I can't operate it in a way where the current in the emitter is not really coming out of the emitter, but it is going inside into the emitter also. I can operate it like that also. What I'm saying is normal operation, when we use it in amplifiers and switches and all that, is where the current is coming out of the emitter. Okay, current is going into the base. So this is NPN and this is PNP. The transistors, so this is a highly simplified schematic. A more realistic picture of transistor is shown over here. A more realistic picture. So what is happening is, let's say the transistor is being made on a piece of silicon. So the piece of silicon is, let's say, P minus. So whenever you see minus, it means very low doping. Normal N or P, it means moderate doping. And when you see N plus, it means heavy doping. Now, what do I mean by heavy? Moderate value of doping, you may keep in mind, let's say 10 to the power 16 or 10 to the power 17. Okay, that's a moderate doping. Anything much higher than 10 to the power 17 would become heavy doping. Anything much less than 10 to the power 17 would be very low doping here. So this is a piece, a silicon wafer or silicon substrate, which is P minus. Then there's a region which is N plus here. There's a region N. Then there is P. Then there is N plus. And this is a planar transistor. Planar in the sense all the contacts are at the top. Note, emitter is here, base is here, and collector is here. Now, how is it you know, the way bipolar transistor will be made is you take a piece of silicon and which is only P minus. There's only boron and is P minus everywhere. Then what you do is you take and create a region which is N plus. You'll see why it is N plus in a minute. You create a region which is N plus, you create a region N, then you create a region P and you N plus and you form contacts. And how are you doing all this N and N plus and P? You are sort of diffusing the impurity from the top. If you take a silicon wafer and put it at high temperature in the presence of a appropriate impurity, the impurity would diffuse into the substrate here and will make that particular region N or P. If you're wondering, how is it that I make only this region N and this region P? How do I maintain that? Well, what you do is at the top, when you are doing the diffusion, at the top you have, silicon dioxide, for example. So silicon dioxide will be present here and not present here. So silicon dioxide acts as a mask. So when you're diffusing the impurity, N-type impurity will not diffuse here because that region is protected, while it would diffuse here. And so that's how you do selective doping. Yes, you're doing selective doping in some region N plus and some region P and some region N plus and all that. Anyway, so processing is an interesting area. How do we make all of these things? That's something that you'll get an opportunity to take a course which will discuss all that in more detail. So this is how the bipolar transistor actually looks. This is again a simplified version. Okay, how it looks. Now you see here the emitter that you see here is N plus. the base is here, P region here, and this is the collector here. Now, why? So these are obvious. Why I need a N region and a P region and an N region here. NPN. I'm trying to make an NPN transistor. That's why we have N, P, and N region here. Now, why did I put N plus? Because normally, as you know, as you will soon see also, that the electrons are injected from the emitter, they flow across the base, and they come to the collector. Now, when they come to the collector, these electrons, they eventually have to go towards the top. The current has to flow. It flows from emitter. The flow of electrons is from here, flows down, but then eventually it has to go here. Now, when it goes here, it has to go like this here. Now, this region, which is N-type, it can have, as it travels here and goes up, there can be a lot of resistance. There can be a lot of resistance, and we don't want these resistances. These resistances, we are not making an ohmic device. You're not making a resistor. So you don't want a resistance, you want a bipolar action from this particular device. So you would like to minimize the resistance, and one way of minimizing the resistance is to add a N plus layer here. So what happens is, the electrons start from here, come down, and they go to the N plus. The N plus provides a nice high doping region, highly conducting region, and the electrons can easily flow across here and then go up. The other thing to notice is the dimensions. The bipolar transistor is not drawn to scale. Not drawn to scale in what sense? Let's start looking at the thicknesses. The thickness of the N plus region here. That's a typical thickness, maybe 1000 angstrom, 100 nanometer. The thickness of the base, 200 nanometer, 2000 angstrom. And similarly, so all these regions are hundreds of nanometer, 100 nanometer, 200 nanometer. This can be again maybe 300 nanometer. So that's the kind of thicknesses that we are talking about. The lateral dimensions are in microns. It could be, for example, the emitter length from here to here. Emitter length, I've said 1 micron. It could be 5 micron. It could be 10 micron. So the lateral dimensions are in microns here, while the vertical dimensions are in hundreds of nanometers. So the diagram is not drawn to scale. So when I say, you may be wondering that I said electrons come here and then they have to travel this particular region. So I put N plus, a highly conducting layer. But then as they go up, what happens here? Well, going up is not a very thick region. It's a very thin region. So it doesn't have as much resistance from here to here as the resistance is in the lateral direction. So that's why an N plus has been put to lower. And by the way, this is simplified. I can have an N plus here also to reduce the resistance and all that here. So when we, the other thing to notice in this diagram is doping level. See, emitter doping is, I'm just giving you, these numbers vary. So emitter doping is very high, 10 to the power 19 or higher here. Note the doping here, 10 to the power 19. The base doping here, 10 to the power 17. And the collector doping, 10 to the power 16. Again, these things vary. I could have collector doping 5 times 16. I could have base doping, which is almost as large as 10 to the power 18 also. It could be. Okay. So these are some typical values that you see here. So if you look at this bipolar transistor, you can clearly see it's not symmetric. It's not symmetric in two senses. One is, note the emitter doping and note the collector doping, N here. 10 to the power 19 versus 10 to the power 16. Highly asymmetric in terms of doping. The other thing which is asymmetric is, look at the emitter area. The emitter area is only here. This green region that you see here. The emitter is much smaller. And look at the collector area. There's the entire collector area here, right? The collector is much larger. If you look at there are two junctions, PN junction that you see here. There's an emitter-based junction here. And there is a collector-based junction here. Note that the junction areas are very different. This is emitter-based junction area is only this much. And the collector-based junction area is much larger. The collector-based junction area could be 4 or 5 times larger than the emitter-based junction area. So the two diodes that you see here, this is a diode here and this is a diode here. They're not symmetrical diodes. They are very different doping and they have very different areas. And that's the because it's asymmetrical. Later on, if we give you a bipolar transistor, let's say if I give you a element bipolar transistor and I ask you to figure out which terminal is emitter, which one is base and which one is collector. Which one is emitter, which one is base, and which one is collector. How do we find out? Well, based on this asymmetry that you see here. We exploit this asymmetry to note, see, there's a clear distinction that base is p-type and emitter and collector are n-type. So that's easy to distinguish by appropriately testing the direction of p-n junction. So that you can please think about how you would solve it. So you can, that you can figure out. But how do you distinguish between emitter and collector? Well, you can see here. Emitter base area is fairly different from collector base area. And the doping levels are also different. Now, think about what the implications of different areas and different dopings are. What would it translate into? Okay, so that's how the bipolar transistor looks like. If you're wondering, why do I have P minus? Why do I have P minus? Why not have just, just start with a silicon, which is N plus and N, and then just make the transistor. The reason, let's see if I have, okay, the reason why we have this P minus, this region here, is that you're not making one transistor. You're making, when I'm making a circuit, let's say the circuit consists of, as an example, 2 transistors, 2 NPN transistors and some resistor and things like that. Now, the 2 NPN transistors, I have to make on the same silicon substrate. And you know the concept of integrated circuit. Integrated circuit means I have to make both the transistors, the resistors, the interconnect, everything on the silicon substrate itself. That's the concept of integrated circuit, that we make the entire circuit on the silicon substrate itself. So if I have 2 transistors, I want those 2 transistors to be isolated from each other. So just imagine in your mind that I have one transistor here and another transistor fabricated side by side. One more transistor. Exactly the same thing. The other transistor also has N plus, N, P, and N plus, and is fabricated by the side of this particular one. Now you can note that the two transistors are isolated from each other. How? How is the collector of this transistor isolated from the collector of other transistor? Well, if you note, how do you go from one transistor to the next transistor? You'll have to go through N plus, P minus, and then the other transistor would also have an N. If you start from one transistor, whose N is here, then you'll have to go to the substrate, and then go to the next transistor, whose N region is there. So what you end up getting is a NPN. You get 2 PN junctions, and both the junctions are kept reverse biased. So the 2 transistors that you see here, one transistor here, another transistor here, they're isolated from each other by 2 reverse bias junctions. And we know reverse bias junctions are, they're non-conducting. Okay, so I'll show you a picture maybe next time, which will clarify it a little bit more. So the reason this is also important, and which also brings us to a point that note that there is an emitter, there is a base, and there is a collector. A bipolar transistor also has a substrate terminal. This is the silicon substrate, and underneath it I have a contact here. So bipolar transistors also have, in many cases you would see a 4th terminal, which is the substrate terminal. And the substrate terminal, note that what I do to this terminal here is that I make it highly negative. I make it negative so that this junction that you see here is always reverse bias. Okay, so we'll see some of those things later on. So when I talk about bipolar transistor, note that what I'm talking about. I'm taking a cross section, a part here in between these 2 dotted lines, and this is what I'm drawing. So when I draw a simplified schematic of NPN, what I'm doing is I'm taking this particular part. This is where most of the action takes place. The bipolar action, the transistor action takes place here. The rest of the regions are for making contact. So this is where the bipolar transistor is. And so in a simplified form, this is what we get here. And then we further simplify it. We don't show P minus. We don't show that. We don't show N plus. And we show something of this kind here. Right? Emitter, collector, and base. So when you see a simplified schematic like this, I mean, if you wonder how am I making a contact on the side of a P-type, you know that the contact is somewhere here, okay? It's not like that. It's just a simplified view of how we show it. Okay, so it should be clear to you where this particular diagram is coming from. This is how the bipolar transistor actually looks. A two-dimensional view here. This is a simplified one-dimensional view. The other part is this is how it may, if you could, if you get a bipolar transistor and you take out its cover, there's a small metal can maybe there, and if you take it out and if you could take a look at it, this is how it may look. Okay, so this is a top view. So you have a silicon wafer and you're looking at the bipolar transistor from the top. Okay, you're looking at it from the top and it may look like this here. See, this region here is emitter. This region here is base here. And this region here is collector here. And then these are making contact to the emitter. This is making contact to the base. Again, these are schematics. Okay, these are schematics. These are simplified. So you're making a contact to the base and you're making a contact to the, this is to the collector and this is to the base here. Okay, so you have three contacts and note that the transistor itself is very tiny. It's a couple of microns. So the transistor is very, very small. So what we do is these very small transistor is so small that it's difficult for you to even see. And therefore, if you want to make circuits by connecting transistors, you can't handle it. I mean, if you can't even see, then you can't, where is emitter, where is base and collector here. So we deliberately package it and make the transistor large. Actual transistor is very small, but we package it and we make it large so that you can see it, you can handle it and all that. So that's part of packaging. So in packaging, what we are doing is we have these big pads of metal that you see here. Big pad of metal here, pad of metal here, pad of metal here. So this is actually making contact to the collector, to the base, to the emitter. And to these pads of emitter, so these are big pads of aluminum or gold, or aluminum, let's say. And to this, then we attach a very fine wire. Very fine wire is attached here, a fine wire is attached here, and wire is attached here. And these are then attached to the pins. So when you see a transistor, these are then attached to the pins of your terminals of the package. So actual transistor is a small, tiny chip of silicon, to which there are these metal pads making contacts to the different regions of the transistor. And to these pads, there are very fine metal wires. Then they make a contact to the terminal. Okay, so that's how a transistor, a packaged transistor may look like. All right, so let's come back now and look at the operation. So the background to understand how a bipolar transistor is acting like a transistor, the background to that is, as we can see, the bipolar transistor is made up of a PN junction. So the background is that if I take a forward biased junction here. So when I forward bias it, what happens is electrons are injected from the N to the P region and holes are injected from P to the N region. These arrows, these broken arrows do not indicate current, but they only indicate the direction of flow. So the current due to electrons obviously is also flowing in the same direction. So the current is in the same direction, but the flow of electrons is from N to the P and the flow of holes is from P to the N. So the total current across this junction, total current which flows, is made up of two components. Electron current component and the hole current component here, IN plus IP. Both of these current components, IN and IP, we saw that this is nothing but a diode, and we are talking about forward bias diode. Both of these current components increase exponentially with voltage. That's the nature of a diode. If you increase the forward bias, the flow of electrons and the flow of holes increases exponentially with voltage here. So both of them are exponential functions of voltage. The other one is, if I make the doping in N region much higher than the doping in P region, then what I end up doing is making this current much larger than this particular current. I can control the relative amounts of electron and hole current. by making the doping in one region larger than the doping in the other region. Okay, so that's why if you note, I've shown the electron flow in a thicker line, meaning that there are a lot of electrons flowing, and this is a thinner line, meaning there are very few holes flowing. So I can do that. In fact, I can make the ratio of electron current to the hole current, let's say, equal to 10 or 100 or 200. I can arrange the dopings and other things in such a way that I can control the ratio here. Okay? So this is the nature of a PN junction under forward bias. Keep that in your mind while we talk about bipolar transistor. All right. So we have now a N plus P junction. So obviously N plus P junction. And what are we doing? This region, we'll call it emitter, we'll call it base. All right. We are forward biasing the junction. You can see clearly. We are applying a negative voltage to the emitter and base is ground. So we are forward biasing the emitter base junction. A lot of electrons would tend to flow and very little holes will flow. Relatively smaller amounts of holes will flow here. I equal to IN plus IP. Fine. Let's look at another PN junction. This is one PN junction. Let's look at another PN junction. Look at this PN junction here. So this is forward biased. Look at what I've applied here. This is again ground, and I've applied a positive bias. So it's a reverse bias junction. Now in reverse bias junction, we know the current flow is very small. And why is the current, so in a reverse bias junction, why is the current very small? Because you're asking electrons to flow from this region to this region. That's the direction in which electrons have to flow. Because of positive bias here is pulling the electrons from this to here. So you're asking electrons to flow from P to the N. And you're asking holes to flow from N to the P. That's what this particular bias is doing. Positive bias is pushing the holes here into this particular region here. Attracting the electrons from here into this particular region here. Why is the current so small? The current is so small because there are very few holes here. Very few electrons here. You're asking electrons to flow from P to the N. There are very, very few electrons here. And that's why very little current flows. You're asking for holes to flow from N to the P region. The holes are minority carriers, very little current flows. So that's the nature of a reverse bias junction here. Reverse bias junction here with very little current flowing here. Right? So we have now two isolated PN junctions. This one here forward bias, this one here reverse bias. Alright, so now what we're going to do is take these two PN junctions and fuse them together. Alright, fuse them together. Okay, the two junctions are taken and fused together here. Now, look at what happens here. This junction is forward biased still. Electrons are being injected here. Right? Now, these two regions are connected. There's one single P region here. One single P region, okay? Forget about this line anymore. There's no line. One single P region here. Now remember, what was this reverse bias junction demanding? It was demanding that electrons flow from P to the N. And there were no electrons in the P region. Now when you fuse them together, this region is flooded with electrons. Where? They've come from the emitter. Emitter is injected and this region now has a lot of electrons. So these electrons, they just flow here. So even though this junction is reverse biased, I start getting across a reverse bias junction a lot of current. Because all these electrons which came into the P region here, they all travel. The region is very thin. We deliberately make it very, very thin. So there are all these electrons that are injected here. Almost all of them cross here. So we get a large electron current. Whatever electrons are injected into the base, almost the same number of electrons flow into the collector. The holes are still flowing like this here. The holes are still flowing here. Is there any other component of current? Anything else which is flowing? Well, in a reverse bias PN junction, we said electrons have to flow from P to the N. Holes have to flow from N to the P. So you're right, there is a hole current here flowing from N to the P. But it's a reverse bias junction, right? And number of electrons in P region, number of holes in this N region is very small. So that's a negligible current. We're not going to show that. Okay? So that's the current flow in a bipolar transistor. Note, electrons injected here, the electrons flow across. Holes are injected from P to the N plus. That's it. Under this bias condition, this is the nature of current flow. Alright? So, straight flow of electrons all the way, it comes to the base and goes all the way to the collector and N plus here. This is what we call as, obviously, we'll call this as the collector. So collector current. So collector current is what? Collector current is nothing but if I call this the electron current. If I call this the electron current due to flow of electrons, collector current will be equal to the electron current. Why am I saying approximately? Because there are other components of current also, but they're very small. I'm neglecting them. That's why I put an approximate sign. Okay. So collector current is equal to electron current. Note, this denotes only the direction of electron flow. The actual current is obviously opposite to that. So IC is equal to IN. What is the base current equal to? Base current is here, flowing from here. What is that equal to? What is base current in this equal to? The emitter current is the sum of these two, right? Emitter current is IN plus IP. Both of them are flowing across and both of them will go here into this terminal here. The base current is what? Note that holes are flowing from P to the N plus. Where are these holes coming from? The base current has to supply these holes here. So base current is equal to IP here, this one. So note all the components of the current that are flowing inside the bipolar transistor. This is simply the electron current. This is simply the hole current here, this green one here. And the emitter current is the sum of these two. And note, what did we do? We made this N plus and P, which means what? IN is much, much larger than IP. IN, the electron current, is much, much larger than IP. So, if I look at the ratio of the collector current and the base current, IC by IB, I get ratio is IN by IP. And we said by making emitter N plus and base P, the ratio IN by IP is much, much larger than 1. I can get a ratio of 100, 50, 200, 250, depending on how I construct my transistor. How I take my dopings and thicknesses and all that. So what I'm getting is a gain, if you would like, I'm getting a current gain in my transistor. The ratio of collector current to the ratio of base current is a quantity which can be much larger than 1. What would be the ratio of collector current and emitter current? Look at the picture. IC and IE would be IN divided by IN plus IP and would be very close to 1. So the collector current, note that because IP is so small, so the ratio of the collector current to the emitter current here will be practically close to unity here. Okay, so the ratios are IC is almost equal to IE. Base current is of course much smaller. But I've still not told you that it's a transistor. Is it a transistor? How do I tell whether it's a transistor? Just because I get IC and IB and IE doesn't make it a transistor. What will make this a transistor? Let's say we call this the output terminal. Collector as the output terminal. Emitter as the input terminal. What would convince you that it's a transistor? IC should not depend on the collector voltage, right? IC should not depend on the collector voltage, but should depend a lot on the emitter voltage. Can we see that? Can we see that IC would depend a lot on the emitter voltage? Because what is the source of IC? The electron current that you see here. Where did this electron current come from? It comes from injection from the emitter. And what did we say? It's a forward bias junction. How does the electron current change with voltage? Exponentially. The electron current here changes exponentially with the voltage here, which means that the collector current that you see here will change exponentially with voltage here. As I change my emitter voltage, the collector current would change exponentially. It's quite sensitive. So that you can see here, that IC is quite sensitive to the voltage that I apply here. The other point is, IC is not sensitive to this voltage. Why? That's important to understand. It's not just that IC should be sensitive to emitter voltage and that will make it a transistor. There's a second condition which must be true, that IC is not sensitive to this voltage. Why? If I increase the collector voltage, what will it do? Will it increase this current? Now you have to go back and recall why. If you, for example, the current across this reverse bias junction, the current across a reverse bias junction does not depend on the amount of reverse bias that you apply. You can make the reverse bias 1 volt, 2 volt, 3 volt. That doesn't do anything to the current flowing. Why? Because note that why is the current small? If we go back again, please keep that in mind. Why is the current small here? Why is the current small here? The current is small because I don't have enough electrons. If I make my collector voltage larger, instead of 1 volt, 5 volt, does it increase the supply of electrons here? No. It can't do anything there. It's easy. In fact, it's not difficult for an electron to go from P to the N region. The electric field, if you look at the direction of electric field, it helps the flow of electrons. So it's not that it's difficult for an electron to flow from P to the N region. That's not the reason why current is small. The reason why current is small is I have very few electrons here. So understand, the bottleneck to current flow is not that it's difficult to move from here to here, is that I have very few electrons here. And by going from 1 volt to 2 volt to 3 volt or 4 volt, I don't do anything to the supply of electrons here. And therefore nothing changes. And that's why when you go back to your bipolar transistor, you can see here that as I change my collector bias, it does not change the supply of these electrons at all. The supply of these electrons is under the control of this junction. This junction is controlling the supply of electrons. This junction doesn't do anything to the supply of electrons. So you can make it 1 volt or 2 volt or 3 volt. Nothing happens to this red arrow that you see here. The number of electrons that flow still remains the same. Nothing really changes here. And therefore, my collector current is independent of the voltage here, collector voltage here. While the collector current here is very sensitive to this voltage here. So thereby you have a transistor action. You have a current which is very sensitive to this voltage. You have transconductance. And you have current which is not sensitive to this voltage. You have very little output conductance. That is what is making it a transistor. Okay. All right. So far what I've been showing is that I've applied a forward bias here. This is ground and I made it here. We could as well arrange the bias condition like this. I could make the emitter ground. I could apply a voltage here at the base, forward bias it, and I could apply a voltage at the collector, which is larger than the base, and this particular junction would still be reverse biased. Okay, so if this is 0.7, I apply 5 volt here. This junction is reverse biased. This junction is forward biased. Same thing happens here. Same operation as before. So this is what we were looking for, right? We said an ideal transistor is something which will give us like this. What did we get? We didn't get this, but we got, can everybody see that we got something like this? We got something of this nature. Why? Well, let me write base, emitter and collector, 3 terminals. Between base and emitter, what do I see? A PN junction. Between base and emitter, a PN junction. between collector and emitter. So there shouldn't be any problem with this view. It's a PN junction. Between collector and emitter, what do I see? Well, you can say, well, I see between collector and emitter one PN junction and another PN junction, but I'm not writing here a structure. I'm writing here an equivalent circuit. So in terms of currents and voltages, what do you see? You see that between collector and emitter, what is there in terms of current? This red arrow, that's right. This is what is there. This is what is linking collector and emitter. The current that you see here, this one. So between collector and emitter is this arrow here. And that's what I denote by a current source is current. And I denote it by a voltage dependent current source. Voltage dependent current source. Between collector and emitter, I denote it by a voltage dependent current source. So we say, yes, look at this arrow here. There's a current flowing. There's a current flowing. And what does this current depend on? It depends on the base emitter voltage. The forward bias emitter base voltage here. So there is a current, and I write down the direction of current, and it depends on base emitter voltage here. And base emitter voltage is where? Base emitter voltage is not across this. It's across a separate pair of terminals. So that's why it's a voltage control current source. It's a voltage control current source. So you can see that it's beginning to look like this. It's not exactly, as we said, we will not get this element. This element is an ideal element that you cannot get. But you've gotten something between base and emitter, fine. There's a diode. You were looking for an open circuit, you didn't get open circuit. Okay, we'll have to live with it. But between collector and emitter, we got a voltage dependent current source, because that's the key element that will make it a transistor. A voltage controlled current source. Okay, but remember what kind of a voltage controlled current source we wanted? We wanted a I0 which is linearly related to Vi. Linear relationship. I0 is equal to Gm times Vi here. We wanted a linear relationship. Well, IC is not linearly related to base emitter voltage. IC is related to base emitter voltage in an exponential manner here. So yes, we got a voltage dependent current source. So we got a current source here, which is very sensitive to voltage here, and is not sensitive to voltage applied across collector and emitter terminals. And in that sense, this is a transistor. Because the heart of a transistor is that this transconductance should be much larger than output conductance. So that's the feature that you are getting there. Okay? So, the transistor, as all of you know, was invented sometime in 1947. All right. Do people know who are well, I should have removed this part. So it's all written here, but out of these three people here, right? Who's the one who's sitting? Have you seen this picture before? Who's the one who's sitting? Who's the one on the left? And who's the one on the right? As electrical and electronics engineers, you guys should also know about the history, how the transistor was invented, who the people were, maybe what they looked like. I mean, you should be you should be interested in your area, in your field, okay? So there is there are a lot of course, if you go and search, there's a lot of material available on the details of the history of invention of transistor. There's a nice set of documentary on YouTube. Please go and watch it. It's interesting as to how the transistor was invented. It also shows you, I told you about emitter, base, and collector. Now, the word emitter is fine. It's emitting electrons. The word collector is also fine. It's collecting electrons. Where does the word base come from? Why am I calling it base? So look at the first transistor. The first transistor, again, as you'll go and read more about it, the first transistor was a big block of germanium that you see here. This block of germanium. And on top of the germanium, two contacts were made, emitter and collector. So you can see that base, that's why it's called the base here, right? It's sitting on the table, is the one which is supporting, and two contacts are being made at the top, emitter and collector. So the word base is coming from the way the first transistor looked. Okay. And the other interesting thing about thing is that I painted a very nice logical picture of how to construct a transistor. I said, take a forward bias junction, take a reverse bias junction, put them together, link the currents together, and paint it as if it's so nice and logical. The bipolar transistor was not invented like that at all. In fact, nobody anticipated a bipolar transistor. The people who invented it, you would see they invented it by accident. They invented it by accident. And after the bipolar transistor was made, they thought of a theory, okay, how to explain what is happening. Okay, so what we have done here, we have just reversed it. We've shown you a very nice way of PN junction here, PN junction here, put them together, and that's how. That's only for the sake of explanation. That's not how things are invented. The invention process is very messy, a lot of false steps and back and forth and all that. So it's very interesting. Go and read how it was invented. There are also Nobel lectures by all three of them, and you can go and read where the transistor, its history, and all that are very nicely explained. Okay.